Have you ever thought about this? The more you try to nail down one thing about our universe, the more another thing slips right through your fingers. It's one of the weirdest, most mind-bending rules out there, and today we're diving into the story of why. This is Heisenberg's uncertainty principle.
So let's just jump right in with a wild idea. What if the simple act of looking at something, observing it, actually changes what it is and what it's doing? And I don't mean in some philosophical way. I mean, what if that's a hard and fast rule of physics?
Because, well, that's exactly what happens down to the quantum level. You can think of it like this. The universe has an unbreakable precision tax. The more precise you want to be about one thing, the more you have to pay up with fuzziness somewhere else.
Imagine you're trying to catch a firefly in a completely dark field. To see exactly where it is, you have to hit it with a really bright, focused flashlight beam. But what happens the instant that light hits the firefly? It gets spooked and zips off in some totally random direction. For a split second, you knew exactly where it was. But now, you have absolutely no clue where it's going. That right there is the trade-off. But why?
To get that, we need to jump back to the 1920s. Physics was in a total crisis. See, scientists were wrestling with this huge problem, the case of the collapsing atom. All the classical physics they knew said that an electron orbiting a nucleus should just lose energy and spiral into its doom. But atoms were obviously stable. The old rules were broken.
The solution came in this amazing rapid-fire burst of genius. In 1924, Louis de Broglie just drops a bombshell. What if particles, like electrons, could also act like waves, spread out and wavy? Then, just 2 years later, Schrödinger gives us the beautiful math to actually describe those waves. And then, in 1927, a young Werner Heisenberg comes in with a final clue that ties it all together. And yeah, that work would go on to win him the Nobel Prize.
And this right here shows you just how big a deal this was. Classical physics gave us Newton's apple, right? An object that follows a perfectly predictable path. But that same logic just failed completely when you got down to the size of an atom. Heisenberg's idea basically saved the day by showing that an electron isn't a tiny planet orbiting a sun. Nope, it's more like a stable smear, a cloud of probability. And its very fuzziness is what keeps it from crashing.
So you see, this blurriness, this fuzziness, it isn't a mistake. It's not a flaw in our measuring tools. It's a fundamental feature of how reality works. The big question, though, is why? Why does it have to be this way?
And it all comes down to one of the coolest ideas in all of science, wave-particle duality. Every single quantum object, an electron, a photon, you name it, is two things at once. It's a tiny, compact little particle, and it's a spread-out wave of pure possibility, both at the exact same time. Okay, so let's think about what happens when we try to measure one of these things. If we want to know its exact position, what we're really doing is taking that spread-out wave of possibility and we're squeezing it, forcing it into a really narrow, sharp spike.
And the very moment you do that, bam, its momentum, which is its speed and direction, just explodes into this huge, uncertain range of possibilities. You get that precision you wanted for its position, but you pay for it big time with total uncertainty about its momentum. It's a trade-off baked into the universe.
And this is the part that really messes with your head. It's not just that our tools are clumsy and we're bumping into things when we measure them. The truth is so much stranger. Before we look, the particle itself doesn't have one definite position and one definite momentum. It just doesn't. It exists as a cloud of what could be.
To really drive this home, Heisenberg came up with this fantastic thought experiment. Let's walk through it together. So imagine we've got this incredibly powerful microscope, and our goal is to see a single, tiny electron. Okay, step one. To see the electron, you gotta shine a light on it, right? But to get a really sharp image, you need light with a super short wavelength, like a powerful gamma-ray photon. Step two. That photon hits the electron, bounces off, and flies into your microscope. Great, now you know where the electron was. But step three, and here's the kicker, that photon just slammed into the tiny electron with a ton of energy, kicking it and sending it flying off in a completely new and unpredictable direction. The more precisely you try to measure its position, the bigger that random kick to its momentum becomes. And this relationship is locked in by this beautiful, profound little equation. The uncertainty in position, that's delta x, times the uncertainty in momentum, delta p, can never, ever be less than a tiny fundamental constant of the universe.
So what does that actually look like? Well, using Heisenberg's microscope idea, trying to pinpoint that electron leaves you with an uncertainty in its position of about 4 times 10 to the minus 13 meters. Now that sounds impossibly small to us, but on the scale of an atom, that is a massive, huge amount of uncertainty.
So why don't we notice this when we're, say, watching a baseball game? Well, a baseball is gigantic compared to an electron. As you can see here, the uncertainty in a baseball's position is a number so ridiculously small it's completely meaningless. But for a teeny tiny electron, that same uncertainty is huge. It's often bigger than the atom it's in. This is why we live in a predictable classical world, but atoms live in a fuzzy quantum world.
So it's easy to think of this cosmic fuzziness as just a frustrating limitation. But what if it isn't a bug? What if it's actually a feature? It turns out, by embracing this fundamental blur, we've figured out how to build some of the most incredible technologies we have.
And I mean, this isn't just theory. It's the stuff you use every day. The computer chips in your phone rely on something called quantum tunneling. Electrons passing through barriers they shouldn't be able to, all because their position is fundamentally uncertain. Electron microscopes, lasers, the quest for quantum computing, all of it is powered by harnessing this weirdness.
And, you know, what's really amazing is how this cornerstone of modern physics seems to echo ancient philosophy. The Buddhist concept of anicca, or impermanence, teaches that nothing in the universe is ever truly fixed or static. Everything is in a constant state of flux. It's just such a beautiful parallel to the quantum world, isn't it? Where reality is just this shimmering wave of possibilities until we decide to look. And that really leaves us with one last big idea to chew on. Maybe this principle is teaching us something profound about reality itself. Maybe it's not some static set of facts just sitting there waiting for us to find them. Maybe it's more like a conversation, an interaction where the universe only reveals an answer when we ask, and the very act of asking changes what that answer can be.